And what that means is that we can say the following. Let's add a note. What we're going to say is that the solution set now, so remember that's the set of all solutions, and let's say the solution set to star, and then this system up here, I'll just label that as star just for reference. So we're talking about the solution set to that homogeneous linear system is given by what? It's given by the span of this vector, right? Remember, the span of a collection of vectors is the set of all linear combinations of those vectors. So if you take the span of just a single vector, well, in that case, a linear combination just means a multiple. So if you take the span of a particular vector, you're talking about the set of all multiples of that vector. So let's abbreviate it like this. Let's say the span of V, and then we could just use V as a nickname for this vector here, -8, -2, and 1. Okay, now let's take a look at what this at the shape of our solution set. Okay, I'm going to try my best to draw a 3D picture here. Okay, so we've got our three axes. I'll label them this time: x1, x2, x3. Okay, so remember what the span of a single non-zero vector in R3 looks like? It's a line. Right? It's a line through the origin, and the way you can figure out which line it is start by just drawing this vector as an arrow. Draw it as a position vector. So this isn't going to be perfect, but I'll do my best. Right? It's got an x1 coordinate of -8 and an x2 coordinate of -2, and then a x3 coordinate of 1. So it's going to be pointing backwards in some sense, like that. Okay. And it's not going to be easy to draw it perfectly because you're trying to draw it on a two-dimensional surface, but that's not too bad. Okay, so it's good to know that it's pointing backwards. It's pointing backwards away from us in the other side of the axes. So I'll label this as V, and then if we want to actually take the span of that vector, well, then we just need to extend it to be an entire line. So extend it infinitely far in either direction. So that's, in this case, our solution set to this homogeneous linear system is actually a line. And here's something to think about going forward. We had one free variable. When we got to this stage, we knew we were going to have exactly one free variable. That means the solution set is going to be a one-dimensional shape, and lines are certainly one-dimensional, right? So keep that in mind going forward, and then try to guess what might happen if you have two free variables. What's that going to look like, okay? And soon enough we'll see. But here's a fact I want to actually spend a moment talking about. So if you have a linear system, ax equals b, that would be the most general matrix equation you could write down. So there's some linear system that corresponds to that matrix equation. If you have any linear system like this at all, ax equals b, you can always take the b and change it to the zero vector, and you're going to get possibly a different linear system, but you're going to get a system that is homogeneous. Right? So every linear system has a corresponding homogeneous linear system that you can obtain just by replacing the constant column with the zero vector. So if you have the following, let's say we have the following. Let's say P is a vector that is some solution to our original linear system, ax equals b, and let's say that V is some solution, any solution at all, to the associated homogeneous system. Well, it turns out that if you add those two solutions together, you're going to get a solution to your original matrix equation. Okay, and it's not magic. It actually happens for a very concrete reason. Let's check. So let's suppose, I'm going to start with some assumptions here, which really this isn't anything other than just a rephrasing of the assumptions that we were given here. So let's suppose that A times P is equal to B. What am I saying there? What I'm really saying is that P is a solution to AX equals B. Because what does it mean for P to be a solution to AX equals B? It means if you were to plug in P for X, then the resulting equation would be true. So if we're assuming that that's the case, if we're assuming that P is a solution to AX equals B, another way to say that would just be to say assume that AP is equal to B. We can do something similar with the other assumption. We're going to assume that V is a solution to the associated homogeneous system AX equals 0. So we're going to suppose, as an assumption, we could say just suppose that A times V is equal to 0. Okay, so these two equations are just translations of what these assumptions are. Okay, well, what does that imply? What if I went like this? What if I how would I show that P plus V is a solution to AX plus B, or pardon me, AX equals B? I would just have to show that if I take P plus V and I plug it in for X, then the resulting equation is true. So let's start by taking a look at that. Let's say we'll look at the left-hand side. I'll go A, and then instead of an X, I'll put P plus V. And let's actually just perform this matrix multiplication and see if we end up getting B. And if we do, then that means then we've completed the proof, and that verifies the fact. So, okay, well, we don't know what the entries of A are, and we don't know what the entries of P or V are, so it may seem like you can't actually evaluate this. But one of the properties that we have is that you can actually distribute this multiplication into the brackets. Okay, so you're going to end up with AP plus AV. And now is where the assumptions come in. Okay, the assumptions, this was equal to B, and this is equal to the 0 vector. So if you were to add those up now, you're going to get B plus the 0 vector. And remember, if you add the 0 vector to anything, you're just going to end up getting, you're not going to change it, so we'll just end up with B. Okay, so that completes the proof. I'll just draw this little box here to indicate that the proof is complete. So that verifies this statement. That's why this is true. So if you have a solution to any matrix equation and you add it to some other solution to the associated homogeneous system, then what you're going to get is another solution to the linear system that you started with. Okay, so that's an interesting theoretical fact. Okay, let's look at another example here. Notice that this linear system, well, it's given as a matrix equation, but it's still a linear system. This is not homogeneous because the constant column does not consist entirely of zeros. So that's worth noting. I left some space here, and then I wrote solution down on the next page. Let me just change that. I'll just erase this, and then we can start the solution here because I want to use this space so that we have enough room on the next page. Okay, so let's start solving this. So what's the solution going to look like? Well, we can just write down the augmented matrix of the underlying linear system, right? So we'll just copy our coefficients: 1, 0, 5, negative 1, 1, 2, 2, negative 1, 3, and then 8, 3, 5. Okay, and well, let's row reduce it. Okay, so we will take row 2 and we'll add row 1 to that, and then we'll take row 3 and we'll subtract row 1 twice, and that will clear out the non-zero entries in the second and third row. So let me just erase these rows. Okay, so what's going to happen in row 2? We're going to have 0, 1, 7, 11, and then in row 3 we're going to have 0, negative 1, negative 7, negative 11. Okay, so, well, that looks like it's nice. Row 3 is just the negative of row 2, so we can just take row 3 and replace it with row 3 plus row 2. And what's that going to give us? That's going to give us the reducer echelon form. Because if I add row 2 to row 3, what I'm going to do here is I'm going to introduce a row of zeros. And actually, you can check that that's in reduced row echelon form.